So Dr. Stephanie Ho is a new postdoc here. She is on the 4th floor, so you guys should go talk to her. She recently earned her PhD from the University of California, Santa Barbara, and she's an expert on the Circumgalactic medium. So through both observations and simulations, she's tackling these fundamental questions about this thing right here, how gas gets into galaxies and cycles through galaxies and then expelled from galaxies. So yeah, we're going to obviously hear more about that today. Before that, though, I want to make a quick announcement, and that is there's lunch after this talk, but there's also going to be a dinner. So if you're interested in dinner, sign up on that Google spreadsheet. There's a link in the last email that I sent out. So currently, Rob is the only one signed up. So hopefully others can join for free dinner tonight.
Either that or we'll have a really nice
dinner.
So thank you for the introduction, and thank you all for coming. I recently graduated from UC Santa Barbara, where I work with Crystal Martin on studying the Circumgalactic medium, and particularly we focus on kinematics. So that is the list of our collaborators, including Glenn Kapsak, Chris Churchill, Monica Turner, and Yoshi. Most of the baryons associated with galaxy halos are not in the galaxy itself, but in the circumgalactic medium. The circumgalactic medium, or the CGM, is a diffuse gas around galaxies and extends to the virial radius. It holds the metal-rich gas flown out in galaxies, as shown in pink in this picture. It also regulates the gas accretion onto galaxies by continuously supplying gas to a galaxy and therefore feed the galaxy star formation, as shown in blue in this picture. Therefore, the CGM is closely related to the evolution of galaxies and the assembly of galactic disk. However, because the gas density is so low, so diffuse, it's really hard to be directly imaged. But still, we can still observe the CGM through absorption detected in the spectra of background quasars. We studied the kinematics of the CGM using 50 galaxy quasar pairs. First of all, we selected a uniform sample of galaxies from the Sloan Digital Sky Survey, such that all galaxies have similar properties. All 50 galaxies are blue star forming and are redshift around 0.2. They all have inclined disk and a similar stellar mass. And for each galaxy, there's a quasar behind it at a small angular separation, such that the quasar sightlines passes the galaxy within 100 kiloparsec from galaxy center, and that's smaller than half of the virial radius. Therefore, all of our sightlines intersects the CGM, or intersects the inner CGM of these galaxies. We then work and interpret the circumgalactic absorption in the reference frame of the galactic disk. We define something called the azimuthal angle as the angle between the galaxy major axis, or this is also the galaxy major axis of this target galaxy, and the line drawing the center between the quasar and the galaxy. So this angle here is the azimuthal angle alpha. We then obtain the spectra for both the galaxy and the quasar. With the galaxy spectrum, we measure the galaxy rotation curve. And if in the field there's another galaxy near our galaxy quasar pair, just as this fellow galaxy here in this image, we will also obtain the spectrum to determine its redshift. And for the quasar spectrum, and this rotation curve, and with the quasar spectrum, we measure the magnesium to absorption. And the magnesium 2 basically traces the cold 10 to the 4 Kelvin gas along the sight line. So for this particular galaxy quasar pair, this is the magnesium 2 doublet that we detected in the quasar spectrum. And if the magnesium to absorption is at the systemic velocity, then it will fall at position at these 2 dashed lines. And for this system, we see that the magnesium 2 is slightly blue shifted because it is shifted to the bluer, shifted to shorter wavelength side. And there's the color bar at the top. It's just showing the velocity range spent by the absorption. The sidebar shows the total velocity range spent by the absorption that we measured. And the orange bar, that is kind of like tiny, you may not see it here, is the velocity range after corrected for the line broadening effect due to the spectral resolution. But what we're going to do next is to look at the galaxy rotation curve and the magnesium to absorption together. So this plot, this blue symbol here represents the magnesium to Doppler shift that we detect in the spectrum. And the color bars just mean the same thing at all. In this particular system, what we see is that the magnesium to is blue shifted. This side of the Galaxy rotation curve is also blue shifted, which means that the magnesium to Doppler shift shares the same sign as the rotation of the galactic disk of the same side. And this phenomenon of this pattern is not just unique for this particular system that I showed here. If we look at more galaxy quasar pairs, when we look at a full sample, this is basically a very common pattern. Gas that is along the sight lines and tens of kiloparsecs away from the galaxy center actually seems to know about how the galaxy disk is rotating. And that gas is actually co-rotating with the disk. So here's our full sample. What we're showing here are all our systems in the reference frame of the galactic disk in the plane of the sky. In the horizontal axis, we align this horizontal axis with the galaxy major axis, and we align the vertical axis with the galaxy minor axis. Each point of the plot represents one quasar sight line. And red color means that quasar sight lines detect magnesium to Doppler shift that has the same sign as the disk rotation. Means that particular sight lines detect magnesium to gas that's co-rotating with the disk. White circles are the points, or are the sight lines that we detect magnesium to absorption at the systemic velocity. Blue points means that particular sight lines we detect magnesium to Doppler shift that is opposite to the disk rotation, which means that sight line is detecting counter-rotating magnesium to gas. And the process just means that particular sight line we don't detect magnesium to absorption. So from this plot here, what we see is that for this region of the plot, we don't see any blue points. What that means is that for sight lines within 45 degrees from the galaxy major axis, we actually don't detect any net counter-rotators. But if we look at sight lines that are nearer to the galaxy minor axis, we see there's some blue points, there's some red points, and we don't see that correlation anymore. Doppler shift, or the Doppler shift that we detected for the magnesium to gas near the minor axis, does not seem to correlate with the disk rotation. So just from our measurements, we already see that the distribution of the magnesium to Doppler shift is incompatible with the random motion in spherical halo. And for sight lines within 45 degrees from the galaxy major axis, we don't find any net counter-rotators. But what does these results mean? How is it related to how galaxy disks evolve? Recall that the chemical evolution of disk galaxies requires a continuous gas inflow. For example, in the plot we show on the right, it shows the gas consumption timescale for a sample of nearby disk galaxies. Typically, the gas consumption timescale is a few gigayears. What that means is that if there's no new gas supply, galaxy will use up their gas within a few gigayears and can no longer sustain their galaxy star formation. So is it possible that the co-rotating gas that we're detecting are actually a gas that's going to feed the disk? And how extended are these co-rotating gas structures are? We don't know where the absorption is along the sight line. But let's consider the hypothesis that at least one of the components of the absorption comes from gas on the disk plate. We then compute the disk radius r at where the sight lines intersect the disk plate. We're showing here, this r here in green. We also compute the line of sight velocity component for gas on a circular orbit. Then we ask the question that, can we use the disk model to predict the velocity of the magnesium to absorber?
Can you go back and explain that? I'm trying to get the geometry in my head.
Mm-hmm.
So your quasar is off the major, it's always off the disk because of some angle.
Yeah.
You're saying somewhere along that line of sight, it's actually crossing the disk plane?
Yeah, so extended display. It's not the display that's maybe like 20, 30 kilohertz.
Oh, of course, because the
It's
disk
like
is.
the display just, you
Yeah,
can imagine
yeah.
the display
In depth.
Yeah, exactly.
Got it, okay, sorry, thank you.
Thank you. So in this plot here, the horizontal axis shows the measured magnesium Doppler shift for our systems. For vertical axis, it shows the velocity that we would have detected if the gas is on a circular orbit on the disk plane. Then the points are showing the quasar sight lines that we detect magnesium to absorption. We color the points by the disk radius r at where the sight lines intersect the disk plane. Lighter color points mean smaller radius. So let's say if we first of all focus on the lighter color points, for example the white points, where the sight lines intersect the disk radius, smaller radius of 70, 80 kiloparsec, we actually see that the measured velocity, so measured magnesium to Doppler shift, actually correlates with the velocity that we would expect to detect if the gas is on a circular orbit. You see the white points around like here, here, yeah. But if we look at the black points alone, we don't see that correlation anymore. Black points are just anywhere. So can we use the disk model to predict the velocity of the magnesium to absorber? No, not all the times, but yes, approximately if our sight lines are intersecting the disk plane within 70, 80 kiloparsec. And if we project our sight lines onto the disk plane, we actually find a high covering fraction for sight lines out to disk radius of 70 kiloparsec. In this plot here, we are projecting the sight lines onto the disk plane. So very early on, I showed you a similar image with blue and red points and white points as well. That is different from this one. That was talking about sky plane. This is projecting the sight lines onto the disk plane. But then the color of the points is still meaning the same thing. Red color still means that the sight lines detect rotating magnesium to end disk. White point still means magnesium 2 is at a systemic velocity. Blue point still means magnesium 2 is counter-rotating compared to the disk. And crosses mean we don't detect magnesium 2 for that sight line. And out of 70 kiloparsec, which is this dashed line here, for sight lines that intersect the disk plane within 70 kiloparsec in radius, we only find one non-detection. The covering fraction is really high, it's close to unity. And then we only find one sight line that detect counter-rotating magnesium 2 gas. So combining this and what we see in the previous slide, what we say is that for sight lines intersecting the disk plane within 70 kiloparsec at disk radius, the knowledge of the rotation curve actually provides a good prediction of the velocity of the magnesium 2 absorber that we're detecting along the quasar sight line. And this quasar sight line is likely to be intersecting an axisymmetric gaseous structure that extends to disk radius of 70 kiloparsec. There's one problem. Although I've been telling you that the gas is rotating with the disk, and therefore that also means that the magnesium 2 gas, or generally we call the low excitation state gas, has significant angular momentum. But the problem is that the magnesium 2 Doppler shift is not high enough to satisfy the condition for gas on a circular orbit. So what is showing in this plot is that the horizontal axis shows disk radius r, but then normalized by halo Fourier radius. Vertical axis shows velocity normalized by the asymptotic rotation speed of the galaxy. And the magenta curve shows the stack of galaxy rotation curves. Cyan point shows the magnesium to Doppler shift after projected onto the disk plane. Black bar, the black color bar, shows the total velocity range that we measured and then projected on the disk plane. Yellow bar shows the velocity range after corrected for the line plotting effect to the spectral resolution and then projected on the disk plane. Red square just shows halo circular velocity at the radius. So the main point here is to compare the cyan point, which is the magnesium to velocity, to the extension of the rotation curve, which is shown in this black line. The magnesium velocity is not high enough, or generally not high enough, to be on circular orbit because it's lower than circular velocity. If this gas is not having a high enough velocity to be on a circular orbit, which means that it cannot be on a circular orbit, so what's the gas doing? One possibility is that it's falling towards the galaxy and beats the galaxy disk. So in order to look closer to the co-rotating gas, we then look at the ego simulation at a similar redshift and for galaxies that's similar stellar mass. This is an example of an ego galaxy. These three plots or these three panels are the same galaxy, but we look at it in different directions. Each point is a cold gas particle, and color points by the line of sight velocity. Blue points means the particle is moving towards us, so it's blue shifted. Red points means the particle is moving away from us, so it's red shifted. So clearly, from all these three panels, we see one side of a galaxy is blue shifted, meaning it's like approaching. The other side is red shifted, so it's receding. So clearly, this galaxy at least, there's a rotating structure. And if we focus on the first panel, we see that look at the distribution of the gas particles. It is distributed more extendedly in the radial direction than in the vertical direction. Which means that for this galaxy, it has a thin rotating cold gas disk that is around a radius of 50, 60 kiloparsec. And look at the scale part here. So honestly, not all the ego galaxies we look at have like thin rotating cold gas disks. This is one of the best examples that we can show. But having rotating gas around the galaxy is not rare, at least among the ego galaxies that we look at. But our aim is not just to look at, hey, yes, we find rotating gas, or no, we don't find any rotating gas. We're trying to understand, or trying to see how the gas gets to the galaxy and feed the galaxy. So this plot here on the left shows the same galaxy. But now we're coloring the particles by how long it takes a particle to reach the inner galaxy. Purple color means particles are in the inner galaxy. Red color, which you can see somewhere here, and there's a streak there, are the particles that would be able to reach the galaxy within a rotation period. And one thing to emphasize that this is colored by the sense that we are doing this prediction using ballistic approximation. And we will talk about that and compare particle tracking later. So this is talking about how long it takes for the particle to reach the galaxy under the ballistic approximation. And now the remaining green particles are the particles that would not be able to reach the galaxy within a rotation period. So if we look at the specific angular momentum for these particles, we show on the right, in terms of radius r. These dots are the particles colored the same way. And the black curve is showing the specific angular momentum required for the particle to be on a circular orbit. And clearly, we can see that for the particles that would be able to reach the galaxy and the inner galaxy within rotation period, which are the red points, are the particles that do not have sufficient angular momentum to stay on the circular orbit. And these are the gas particles that would be able to feed the galaxy and fuel certification.
Are you going to explain the green later? Or?
No,
So
sorry,
most of your particles are below the rotation curve. You're going to talk about that later and are infalling. I don't know what that means. Not infalling.
No, I'm saying what I'll explain later is like this is showed colored particles by whether they reach the galaxy, inner galaxy within rotation period under the assumption of ballistic approximation.
Yeah. Okay. We'll get back to that.
So now here, now here we'll look at some inflow properties, and we're going to compare what we find from the ballistic approximation to what we see from tracking particles within the same time period. So we're going to look at two inflow properties, which are the average radial inflow speed and the mass inflow rate. So we look at this plot here on the left. We focus on the cyan circles. So the horizontal axis shows the average radial inflow speed from particle tracking. vertical axis shows average radial inflow speed from the ballistic approximation. And we see that when we compare the results we get from the two methods, they typically agree with each other within a factor of 2. But regardless of which method we use to look at average radial inflow speed, we still find that typically the radial inflow speed is around 20 to 60 kilometers per second. And that is for the mass inflow rate. Again, look at the left plot and focus on the science circle. Horizontal axis is the mass inflow rate from particle tracking. Vertical axis is the mass inflow rate from ballistic approximation. Again, the two methods usually yield the m dot within a factor of 2 agreement, although particle tracking typically overestimates. But most importantly, we want to see that whether the mass inflow rate is high enough to sustain the galaxy star formation activity. Therefore, on the right, what we're showing is the star formation rate in the horizontal axis. And in the vertical axis, it's going to be mass inflow rate. And depending on symbol, for example, the blue circle is the ballistic approximation, and particle tracking is going to be the red diamond. We're comparing the m dot, the mass inflow rate, and the galaxy star formation rate. And this black dashed line here is the one-to-one relation, meaning the star formation rate is equal to the inflow rate. So we see for most of the galaxies, the mass inflow rate is going to be higher than the star formation rate. And you see there are some green lines there. It's just different models of equilibrium model that take into account the fact that some of the gases removed from galaxies due to outflow and then some of them is recycled back. But anyway, in general, the average mass inflow rate is comparable to the galaxy star formation rate. So it seems to suggest that for these evil galaxies that we look at, the inflowing gas seems to be having high enough inflow rate to sustain the galaxy star formation activity. But then let's go back to observation. Can we actually measure the inflow speed? So what we're going to do is to at least use some symbols to set constraints on the inflow speed, because it's impossible to directly pinpoint the inflow speed at the quasar sightline, just like a pencil beam at one point around the galaxy. So this is the model, which is a radial inflow in the disk plane. What that means is that we have the disk geometry, we have a rotation component for velocity, and we also have a radial inflow component. There are two reasons why we include the radial inflow component. Number one, from earlier observational results that we showed you, we showed that the magnesium to Doppler shift is not high enough to be on circular orbit, which means that the gas cannot just be simply rotating forever in a circular orbit on the disk plane. But the other reason is that it's based on another problem we find in our observation, is that the magnesium to velocity range actually spans a very wide velocity range. Even after corrected for the line broadening effect due to spectral resolution, it's very typical that we find velocity range of 100 kilometers per second or even more. And that type of velocity range is impossible to be explained by a thin rotating disk alone. And that's the motivation why we add radial inflow in this model. Then in order to use a simple model like this to explain magnesium to velocity or magnesium to kinematics that we measured along the quasar sight line, we also need to know the orientation of the galaxy disk on the sky. So at this particular ratio of 0.2, mostly when we look at galaxy images, for example from the SDSS, what you see would be a galaxy looks like an ellipse, and then you can measure this axis ratio, you can measure the galaxy major axis position angle. But that leaves a degeneracy of which way the galaxy disk is tilted on the sky, whether it's like this way or the other way. And then apparently which way the galaxy disk tilted on the sky affects how the two velocity components add together and changes the resultant velocity predicted by the model. And that particular degeneracy in terms of which way the galaxy disk tilts can be resolved if we have the measured galaxy rotation curve. we know how the disk is rotating. And if we can resolve the spiral structure of the disk, this is just an illustration, and now we will go to an example. So what we are aiming at doing here is to combine the radial inflow model and the measured orientation of a disk to reproduce the velocity range spanned by the magnesium absorption that we detected in the quasar sightline. So we can go through an example like this to tell you what exactly I'm trying to do. First of all, here this color image on the left is one of our galaxy. So this color image is combined from two bands in the HSD images, F390W and F840. We also combine that with the KS band image we obtained from Techno 2 with adaptive optics. So this is clearly much better image quality, much higher resolution compared to SDSS image. And what we can see here is the spiral arm structure, which might not be seen easily here, but like I can assure you that it's there. Like there's a blue spiral arm like this way and going that way. And this is illustrated as in the schematic diagram and here. And because from earlier measurements, we already obtained the galaxy rotation curve, we can then deduce which way the galaxy is tilted on the sky, as shown in this image or this picture here. And the orange arrow points to the direction of the quasar sight line. So our aim is to use this orientation that we deduced, combined with the earlier simple radial inflow model to reproduce the velocity range that we measured along the quasar sight line. And that velocity range that we measured along the quasar sight line for this system is shown in the blue cyan bar here. It's like spanning around like 200 kilometers per second, but this in the measured is in terms of the directly measured value. It's not corrected for the line floating effect by spectral resolution.
Sorry, so
Yeah.
an inclination of 0 is like a face-on over
Yes,
to
yes.
the side.
Yeah.
And then so negative would be the lower part is farther away
Yeah.
from us.
Yeah, just look at the other way, and just that's how we define it as positive and negative. But positive and negative just means that either flip one way or the other way.
Okay.
So basically, it just changes how the angular momentum factor is pointing to the direction of the angular momentum factor. Yeah. So in these three panels here, the cyan shaded region shows the total velocity range spanned by the magnesium 2 absorption along the quasar sight line. And the black curve shows how the modeled line of sight velocity changes along the quasar sight line that intersects the extended disk plane. And if the y-axis equals to 0 is where the sight lines intersect the extended disk plane. The black shaded region around the black line, it just aims to reproduce the effect of the line floating effect of the spectral resolution. So if we look at the leftmost panel here, this model is the simplest. We only have a rotating disk, no inflow. What happens is that the absorption predicted by the disk, by this rotating disk model, we create an absorption that is too blue and disk plane, like in this region here. It is like too negative compared to what we measured in the side shader region. So this just a simple rotating disk model failed for this particular galaxy quasar here. But then now let's add the radial inflow component. So as I said earlier, changing how the disk split will changes how the two velocity components add together and give different velocity prediction. So let's say if the disk is split in one particular way, this is how we define as like a positive discontinuation. For this particular case here, if we add a radial inflow component, which is shown in this magenta line here, if we add that to the rotation component and shown in blue, we actually create an even bluer absorption near the disk plane. Because both velocity components have the same sign near the disk plane. Therefore, when we add them together, it becomes even bluer. So this version of the problem, the mismatch problem is even worse. But then if the disk is flipped the other way, what we can see here is that now the sign for the Doppler sign for the rotation component, which is shown in blue, and the sign that is from the radial inflow component, which is shown in magenta. They have opposite sign compared to systemic velocity near the distal plane. Therefore, when we add the two components together, we can eliminate the absorption that is like too blue compared to what we see previously. You see like it's not as blue compared to the previous cases. So for this example, if we only look at this modeling, we would say that, hey, I want the negative disinclination configuration because that allows me to reproduce the velocity range of the magnesium to absorption. But unfortunately, that is not the case for this particular example. What we deduce from a rotation curve and a spiral arm structure is that it has this particular orientation, and we name that as like positive disinclination, and that is actually this case. So what this means is that mean that like, hey, like we learned nothing from this example? No, actually, like what this tells us is that this particular example, we can rule out radial inflow detection along the quasar sideline. And which also means that it is possible that our quasar sidelines is not intersecting just an extended disk. It could be included some satellite contribution, or maybe we're intersecting an inflowing stream. And that is something that we want to answer in the future by having higher resolution quasar spectrum that allows us to better resolve the magnesium absorption component. So okay, the model seems to not work for this example, but we learned something. Here's just another example in the sense that we have the Galaxy rotation curve, we see the spiral arms, this is to deduce disorientation. And what is different in this case here is that if we only have a rotating disk model, it can marginally reproduce the velocity range spent by magnesium to absorption. So what we are seeing here is the like black shaded region actually kind of match with the cyan shaded region in that. So it means that just a rotating disk, yes, it could marginally recreate the velocity range spent by magnesium to absorption that we detected along the sideline. But does that mean that it definitely rules out radial inflow? Not at all, in the sense that what we try to see later is to see whether our model allows some degree of radial inflow. And in this particular example here, what we're showing is that if the disk is tilted in this particular way, which we call the positive disinclination, it could allow radial inflow of at most 40 kilometers per second. If we add radial inflow that's higher than that, we will push this absorption towards the blue direction, so it will create absorption that will be too blue at the distal plane. Therefore, if the disk is oriented this way, we cannot have radial inflow larger than 40 kilometers per second. Similarly, if the disk is tilted the other way, which we call the negative disinclination, then we can add radial inflow up to like 80 kilometers per second before the absorption becomes not blue enough to create the measured velocity range. Therefore, the fact that we deduce the disk as positively inclined actually allows us to set a tighter constraint on the radial inflow speed with our model to 40 kilometers per second instead of 80 kilometers per second. So in summary, the main message of this talk is to tell you that the low ionization state gas in the CGM has significant angular momentum, and any modeling of the CGM should take that into account. Galaxy disk grows inside out, and it's typical to see that the outer galaxy disk is bluer, just as these galaxies that we found, these galaxies in our sample, that you see the bluer spiral arms and bluer outer disk, which also means that the outer disk is younger. So how are results related to how galaxy disk grow? First of all, we find that most of the absorption components that we detected in the quasar sidelines are subcentrifugal. We detect magnesium to Doppler shift that are not high enough to be on circular orbit. Therefore, the gas cannot stay in a pure circular orbit, and therefore it's falling into the galaxy, and therefore it is possible to feed the galaxy disk. And on the other hand, we look at evo simulation with galaxies with similar stellar mass and similar redshift, and we find that it's generally common to see rotating gas structures around these evo galaxies. the inflow speed is typically around 20 to 60 kilometers per second. And by looking at the average mass inflow rate, regardless of whether we use particle tracking or whether we use ballistic approximation, we find that the star formation rate is approximately equal to the mass inflow rate, suggesting that the east inflow gas could feed the galaxy. Therefore, by combining the results of our observations and the simulations that we look at, it is possibly suggesting that the rotating CGM that we detected are actually inflowing gas. Therefore, the gas will feed the galaxy disk, fuel the next generation star formation, and therefore grow the disk eventually. So what I've presented so far are things I've done from the past few years. So what I'm going to briefly talk about next is things that are open questions or future work that I'm hoping to pursue. So observationally, our result shows that the magnesium-2 gas, or low annotation state gas, rotates through the disk. But did it tell you how does these gas look like? What's the morphology? Is it a disk, a thin disk, not a thin disk, but quote unquote quote thin disk, or cylinders, or is it really just inflowing streams? We can tackle this problem or try to explore more on this issue using two methods. One is by gaining more insight from looking at the ego simulation. So I'm going to show you something that's super preliminary. So this is a projected magnesium-2 column density for a galaxy in ego simulation. So we define the orientation of the galaxy using an angular momentum vector. And we project the galaxy from edge-on to face-on view. And we look at the magnesium-2 column density map. And we see that if we project the galaxy in the edge-on view, the magnesium-2 distribution is more like it's very disk-like. It's definitely not a sphere. And the morphology or the observed column density distribution changes when we change the viewing angle of the galaxy disk. So at least this example here shows you that the magnesium-2 distribution, at least in the ego simulation, is disk-like instead of looks like a sphere, a randomly moving gas. But this is just one galaxy. We want to stack more galaxies together to look in general, how does it look like? So here is what we're trying to do to stack the galaxies together. The two rows are just stacking galaxies for the higher stellar mass spin and lower stellar mass spin. From left to right is to try to stack the galaxies together in the sense that they're projected in the same disk inclination angle. What we're trying to see here is where is the region of the magnesium, where's the region around galaxy center that we most often detect magnesium-2, or what is the general distribution? The color map here is showing the fraction of galaxies in this category with the stellar mass range. This category, the fraction of galaxies that detect significant magnesium-2 at that particular pixel. So, for example, if we look at the light blue region, which is near the center, nearly all galaxies detect magnesium-2 over a certain column density limit, which is try to mimic observation that we could detect magnesium-2 at that column density. So if we try to project the galaxy edge-on, and that galaxy orientation is defined by an angular momentum vector, and you see that okay, the distribution is more it's flattened. It's not like a thin disk, but you're definitely not seeing a circular pattern. And that particular, you see the contours, basically the shape of contours changes with how we try to project this in some sense. And as I said, the top row is for the stack of galaxies with lower stellar mass spin, and here is for the high stellar mass spin. Another thing that we clearly see is that more massive galaxies has more extended magnesium-2 that can be detected, because you see it just out to long. If you try to look at a region of where 50% of galaxies has magnesium-2 at that region, it's going to be around 50 kiloparsec for the lower mass spin, but it's going to to be like 75, 80 kiloparsec on high mass spin. So this is about the magnesium 2 distribution, and we also have another plot showing to look at the rotating magnesium 2 gas in Eagle simulation. And at least qualitatively, we see that the rotating gas, okay, the color bar showing the fraction of galaxies in that category that detect rotating gas, rotating magnesium 2 gas. So red color means that like most of the galaxies in that stack detect magnesium 2 gas rotating the disk. And they're mainly concentrated in the horizontal axis here, which is the galaxy major axis. And it's definitely not a uniform pattern. It definitely depends on the disinclination angle, and it's more elongated along the galaxy major axis than the minor axis. But anyway, this is one of the methods of like when we could look at Eagle simulation to gain some insight on the magnesium 2 distribution and kinematics. Another method is to go back to the observation and go to take higher resolution Fraser spectrum. So currently our sample, when we take the Fraser spectrum, we obtain that from CAC LS, which is low resolution spectrum. The spectral resolution is like 100 kilometers per second to 150 kilometers per second. It varies from our observing run. But anyway, what that means is that like for each sight line, it could intersect multiple components. It could be intersecting inflows plus the disk, outflow plus the disk, inflow plus outflow plus the disk, or with streams like or combinations of any combinations of all of these above. And the problem of having low resolution spectra is that they basically just blend every components together. So with high resolution spectrum, what we could do is to resolve the magnesium 2 absorption into components, and then we can model each component separately. At least we can distinguish possibly inflow, outflow, streams, disk, etc. Yes.
I'm going to ask about that later, but the Eagle simulations, do they have enough velocity resolution to give you that some insight into what you expect to see?
Yeah, like it's definitely like a few kilometers per second is definitely fine, but you're not expecting like 0 point something that kind of velocity resolution.
Okay.
Yeah.
Do you see the multiple components in the higher resolution data that is blended at 100 kilometers a second?
Eagle simulation, you mean like you mean spectrum?
Yeah.
Spectrum wise, possibly no. That's why if I'm showing you like
Right.
2D, like there are 2D like column density maps, and like I'm just looking at the Doppler velocity basically.
This is projected,
Yes.
everything in a column.
Yeah, column density weighted line of sight velocity.
Right.
There's-
Since you started, I'll follow up.
Sure.
If you would show
Yeah.
ISO velocity contour map, is it just noise everywhere? It seems to me you should be able to rule out cylinder would mean, right, it not only rotates at the same speed as the disk, but at the same direction. And that to me, intuition says, why should that be? I mean, to what extent does Eagle allow you to, do you think the Eagle simulations are going to allow you to separate? It isn't just essentially every cloud. It's all rotating, but with a wide dispersion of inclinations, et cetera, versus something quite ordered that really knows about the disk.
Yeah, but like this Eagle is this like SPH simulation, so it's basically particles by particle, and each particle covers the velocity. So we can like if do not want like okay, you can look at like particle by particle and just look at velocity factor and try to determine like how coherent that is. Or you can make these projection maps to look at like just column density weighted line of sight velocity. And I think, for example, maybe this plot may answer your question. In the sense that here we're trying to look at like the line of sight velocity, that's column density weighted, and then look at the Doppler sign, and try to see whether it follows the expectation of at least the sign of the rotating disk. And we see that like, for example, for regions like far above the disk plane, the rotation is more like along the galaxy major axis than like just a solid cylinder. Like it's not like everywhere like a cylindrical like contours that shows you equal portion of rotation or something. So like even before we go to look at specifically the exact velocity we're looking at, even just looking at the sign of the Doppler shift, we already see that like it's definitely not just like a solid cylinder doing something like that.
Right. Yeah, because I mean, I think as soon as the real system departs from that, you're gonna get clouds running into each other. Maybe that's a big source of your infall, right? Because, you know, maybe it isn't cosmological infall. If the system of clouds has a significant dispersion orbits, you're just with cloud collisions, I would think you're going to start dissipating that. Anyway, sorry.
So before, because we were talking about resolution earlier, basically brought up both a great spectrum. Originally, I actually planned to do that, but then later on, I realized that if we want to look at these spectrum along a sight line, Eagle simulation may not be the best place to look at. There are definitely much higher simulations, and the better simulation that we look at. There are some currently in this past year, there's some CGM dedicated high resolution simulation that could try to enhance the CGM resolution, which typically when we run simulation, we have the highest resolution in the galaxy disk, the densest region. But then now there's some forced resolution simulation. They try to force the CGM to have higher resolution. But yeah, there's several groups doing that, and I think those are simulations that are better to do synthetic spectrum to look at which component by component in simulations. Okay, so there's the first point. The second point is that okay, the result that I presented is talking about the low ionization state gas, the magnesium-2, which is tracing the cool 10 to the 4 Kelvin gas in the CGM. So if the magnesium-2 gas or the low ionization state gas is co-rotating with the galaxy disk, what about the highly ionized oxygen-6 gas? So oxygen-6 is highly ionized as oxygen-5+. What it's tracing is the warm hot phase in the CGM at 10 to the 5.5 Kelvin. This particular ion, or this particular phase of the gas, has received a lot of attention in the CGM community just because it is quote-unquote weird compared to the cold gas. For example, it is ubiquitously detected around blue star-forming galaxies, but not really in red galaxies. And it can be detected out to 150 kiloparsec away from the galaxy. So it's extend to a larger distance compared to cool gas. And its column density, or equivalent width, that's what we measured, is not dropping as rapidly with impact parameter compared to you look at magnesium-2 cool gas. So oxygen-6 is a hot topic right now. People are trying to understand more about this phase, its origin, how is it ionized. Therefore, it would be interesting if we, instead of looking at all these seems to be big questions, we can also go back to look at the kinematics itself. Is it doing the same thing as what the cool gas is doing? Is it the cool gas is co-rotating with the disk? How about the warm hot phase of the oxygen-6 gas? So we actually recently got 25 orbits to look at several systems for these systems that we observed earlier with magnesium-2. And what we're going to do is to use the HSD Hall spectrum that we actually expect to detect oxygen-6 in those quasar spectrum. Because according to the more famous Halos result, this particular survey, what they're finding is that oxygen-6 is ubiquitously detected around blue star-forming galaxies. And because our galaxies are selected galaxies with blue star-forming as well, we're definitely expecting we're going to detect oxygen-6 absorption. And we're going to study their kinematics, and then also combine them with some of the galaxy quasar pairs we find from the archive. And we're going to combine them and try to better analyze the oxygen-6 kinematics and how is it related to the galaxy disk. There are other questions that I hope to be able to answer in the future as well. Is, for example, what is the origin of the co-radiating gas? Is it from recycling wind? Is it freshly accreted materials? Are there mainly satellites that accrete on the galaxies? And also it would be interesting to look at the chemical abundance pattern and the evolution of the galaxy disk and the CGM and see how they're related to each other. So this is what I prepared for today. And thank you everyone here for listening to my talk. And I'm very happy to be here, and I'm hoping to learn from each other. And I'm happy to talk to anyone who's interested to my previous work, my future planning work, or any new work, or any science topic that anyone is interested to talk about. Thank you.
All right, does anyone have any other questions? Oh, sorry.
is cost high enough resolution that you think you'll be able to start to separate out the different components of oxygen?
Yeah, like whole spectrum resolution is around like several tens of dollars again. So it's not as good as something like high-res, but like because oxygen 6 is in the UV, so like you can't observe it from the ground, so you have to go to HSV cost. So yes, it's not going to be like doing as a nice job as like tech high-res if you were meant to, but at least it's definitely not one broad velocity component that we're seeing right now. But sorry.
No, go ahead.
But like according to some spectra that is like published by the Costello's team, what they see is that like oxygen 6 in general has much broader velocity, just like the absorption are much broader comparing to like the low end CSG. But yes, if it is like going to have components, it is able to resolve it.
Could you use